nonpolar. What's the difference between polar and nonpolar? Okay, I'll help you out. Which one shares electrons equally? Raise your hands. Which one shares electrons equally? Great. Nonpolar, they share equally, right? Equally. All right, Grant, what about polar? Unequally. They create poles, like positive, negative of a battery. Okay? They create poles because things aren't equal. Okay? What? Right. Water is polar. Remember from yesterday? Water is polar. Water is polar. Water is polar. Pantas, right. I saw that. Pantas. We invented that yesterday. I chuckled about that yesterday driving home. Anyways. Yeah, poles here, that means they're not equally distributed. So you should have written down over here, not equally or unequally distributed. Is that true?
Yeah.
Yes, okay. Here we should write equally distributed because everything is shared equally over here.
Yep.
Which one is symmetrical?
Nonpolar.
Nonpolar. Give me a shape that's symmetrical on the X and Y.
Square.
Square, circle, good. What about this one?
Triangle.
Trapezoid.
The word.
Oh.
Asymmetrical, right. So like a triangle, okay? Trapezoid. Rhombus. So, what else am I forgetting? I'm trying to list everything we wrote yesterday.
Not equally distributed.
Yep, said that. Balanced, balanced. This is not balanced. This is balanced, okay? I was trying to use Kerf as an example with the basketball. When we were both holding it right in the middle between us, we were sharing it equally. That's here. But when I kind of had the big grip there on the ball, that's more polar, where one atom kind of has more of it because it's not perfectly shared equally here. And the goal today is to kind of understand that better. All right?
And
Right. Larger difference in electronegativity, smaller difference. And now I'm going to get to that today, right now. So the examples I gave you, water is polar. NH3, what's that called? If you don't know it, write it down. It's ammonia. That's ammonia. You should know that. You need to know it. Write that down. Ammonia. Okay? HCl, hydrochloric acid. I gave that to you, right?
Yeah.
PCl5.
Yeah.
And then N2O?
Yeah. N2O and SF3.
SF3. Okay, those are the ones I gave you?
Mm-hmm.
All right. Over here, CO2,
Yep.
CH4,
H2.
H2, CCl4,
O2.
H2O2, and then O2.
Yeah. And then Br.
All right, I'm just going to do this. All the Honkel-Briffs, all of them are diatomic, obviously. They are nonpolar. Why? Because they are very symmetrical. It's just two little spheres, two little atoms bonded together. You can't really get any more symmetrical than two circles bonded together. Not really. It's very symmetrical. They share everything very equally because they're identical. Imagine playing tug of war with yourself. All right, no one would ever win. That's the point. Over here, nonpolar, when they're kind of fighting over those electrons, no one really wins the battle over those electrons because both sides want the electrons, and since it's symmetrical, no one has an advantage. Over here, they're fighting over electrons, but somebody's going to win slightly. They're going to share, but someone's going to win and share more of it, more of the electrons, because it's not symmetrical. So we're going to learn today how to draw these things and how that's going to help us identify polar and nonpolar. Did we talk about the subscripts?
No.
We did not. Okay, we need to add that. All right. So over here on this side, we have odd subscripts. I'm going to say at the end. And then over here, I'm going to say even subscripts at the even subscripts. When I say at the end, I mean at the end of the compound, at the end of the formula. So odd means polar, even means nonpolar. I'm not a huge fan of teaching that, but over the years I've noticed kids kind of remember that. That's something that registers with them, so I go with it. Because if it's a multiple choice question, that works. Which of the following is a nonpolar covalent molecule? If you remember the even, 2, 2, 2, 2, 4, 2, 4, right? All even. Or which is polar? 1, 3, 1, 5, 1, 3. So the last subscript, the one that it ends with, not the 2 in water, but the one at the end, that's what's going to help you. If it's even, it's nonpolar. If it's odd, it's polar. Why does that make sense? Based on everything we just went over again. Why does it make sense that the nonpolar sharing equally are even, the polar share unequally are odd? Because they're odd numbers. It's hard to split things up equally among odd numbers or odd number of people. Does that make sense?
Mm-hmm.
Like when I'm making groups in lab, sometimes there has to be a group of 3 because I don't have an even number of people. I can't distribute the groups evenly. So even numbers distribute evenly, odd numbers distribute unevenly. Make sense?
Yep.
Oddly? I almost said that. I was thinking. Alright, so let's look up the electronegativity of some of these here, and we're going to write it. Hopefully you have room next to it. What's hydrogen's electronegativity? Brian's got that one. Someone look up oxygen. What about Thomas? Okay, I'll look up nitrogen. Germ, look up chlorine. All right, Brad, what do we got for H?
2.2.
2.2. Thomas, for up?
3.4.
3.4. All right, nitrogen.
Wait.
Okay, it's number 7. They're not, or numerical order.
Electronegativity?
Yep.
3.
3. CL?
3.2.
3.2. Okay, let's just use those 3 examples, okay? So water is 2.2 and 3.4, ammonia is 3 and 2.2, H is HCl, 2.2, 3.2. All right, if I subtract these numbers, what do we get for water? 1.2. If we subtract ammonia, what do we get? 0.8.
Oh.
It's okay. And this one is just 1. Okay. Now let's go over here. Let's look up CO2 here. We'll do CH4. And then we'll do, then we'll talk about the diatomic. So someone look up carbon for us. We already have O and H. H is 2.2. O is 3.4. Yeah, 2.6. Okay. What's 3.4 minus 2.6? 0.8, right? And then this is 0.4. I know I'm going quick. Try to stay with me here. Amanda, you're smart. What if I looked up the electronegativity of the atoms in each of these? So, does that screw you up?
Yes, that's okay.
You got seats here. It's up to you. You sure?
Yeah, I can see.
Okay, or you can move the desk. You can go wherever you want. How about that? Free reign.
Okay.
So you have H's, O's, and so if you have 2 H's bonded together, or 2 O's bonded together, 2 N's, and I looked up the electronegativity, and I subtracted those numbers, what would it be? I'll let you get settled.
Okay.
You guys should all be thinking this. What is the difference in electronegativity in a molecule of H2, or O2, or N2? If I look up the electronegativity of H, and then of H, and then I subtract them, what's it going to be?
Oh, 0.
0. Why?
Because you're just subtracting.
It's the same number subtracted from itself, right? So these here are as purely nonpolar as you can get. The difference in electronegativity is 0. Difference is 0. I'm not writing the I'm not giving a whole lot of notes there because I'm just assuming, maybe I shouldn't assume, but I'm assuming you're following me and you understand what we're doing here. So what am I trying to show you? Well, if I pick these 3 polar molecules, which are really common, they're all around a 1. 1, 1.2, 0.8. These are much lower. Yes, that's 0.8. Okay, same as this. But this is 0.4 and those are 0. So in general, nonpolar, the atoms have very similar electronegativity. If that's the case, again, the tug-of-war analogy, if they're playing tug-of-war and they're similar strengths, no one's going to win. They're going to share equally. The electrons will be right in the middle. Here, Cl is going to pull the electrons a little closer because it's stronger than H. Nitrogen is going to pull it a little closer because it's stronger. Oxygen is going to pull the electrons closer. It's a little stronger. So even though they're sharing, it's unequal sharing. Somebody sort of wins that tug of war, whereas here, it's a stalemate. More of a stalemate. Why? The electronegativities are closer and they're symmetrical. So it's both of those things kind of going at once here. You can't really tell if it's symmetrical looking at it here. That's why we're drawing dot structures. All right, that's what we're going to do the next like 15 minutes. It takes a while to go through these. Questions? So, can you look at these formulas and tell me, okay, that's polar because it's a 5. That's polar because it's a 4. I mean non-polar because it's a 4. If you can, that's great. Doesn't really help on a short answer question, but it helps on a multiple choice. Now we're going to try and get into more in-depth. Can you explain it, draw dot structures, and do that. All right? So here we go. Okay, draw me the dot structure for water. You can start doing that while I'm getting situated here. Draw the dot structure for water. H2O. I'm going to draw 4 dot structures. Water is one of them. NH3 is another. We'll go CCl4, and then we'll do F2. Those are our 4 dot structures we're going to do. Go ahead and do water. If you are confident and you want to move on and do them all, go ahead. I'm going to walk around and see how we're doing. You can take notes through the iPad.
I was trying to, but I couldn't see.
Yeah, it's hard to see. Oh, you're going to town over here. Good
Is
job.
that right?
Yeah, looks good. Remember, we're dealing with covalent here. So how is it different than ionic? What do they do with their electrons? They share. What do ionics do? Transfer. So ionics transfer, so there's charges. Here there's no charges. So we're not putting any charges on these dot structures. Let's see. Jojo, how many dots is oxygen? How many? 6. How many dots does hydrogen? 1. Good.
Are we supposed to be doing dots?
Say it again, Raquel.
Are we supposed to be doing dots?
Oh, yeah, we're doing dot structures. Yes.
You looked at my paper and didn't even tell me I was doing the wrong thing.
Correct. Figured it out.
I am.
You guys are all pretty much on track here. Remember, water looks like Mickey Mouse, right? So last time I checked, ears were not on the side of his head, or on the top. But what you're doing is good stuff. That's fine. I like what you're doing. Good job, obviously keep doing the dots. What? Who's talking? Mickey Mouse is gonna be sideways. CCl4 gets a little crazy. Why?
Well, they're
A
all
lot of
negative.
dots.
Right.
I would use X's for carbon myself and dots for CF. But we'll get to that. All right, you guys are all doing pretty well. That's good. It's good to see. I don't think anybody did this wrong. What I mean by wrong is this. Water does not look like that. Okay, the H's are not opposite. It's either side and top, side and bottom. They have to be at angles to each other. They're not going to be straight across from each other. This is how I explained the period too. You guys honestly got it. It's good, but I'm going to give you the same instruction. The first time we learned dot structures, if you remember, I said you have to do it the way I do it. You go 1, 2, 3, 4, 5, 6. If you do that, 1 dot per side, then the H's will never be opposite. They will always be side, bottom, side, top, whatever, where they're supposed to be. Water is supposed to look like this. That's called a bend. It looks like a V, sort of. Almost looks like a right angle, but it isn't. This angle is actually 104.5 degrees. That's what water is. So if you take, I'll show you water actually. Here it is. Here's water. So there's water. Okay, it's not 90 degrees. It's not 90 degrees. It's supposed to be more like that. But there's water. There's your 2 H's and there's your oxygen. Okay. So it's called a bent molecule. That's the shape of it. It's not linear is like a straight line. There's linear molecules. This is linear. This is called tetrahedral. This is called trigonal pyramidal. You don't need to know that in Regents. AP though, we learned that. We talk about it. Anyways, the point is water needs to look like this. Why, Kerf? Why does water look like this? Because it's what type of covalent? Polar, because water's polar. If water had the H here, would it be symmetrical?
No.
If the H was here, would it be symmetrical? Yes. Symmetrical is for nonpolar. This is asymmetrical. How is it asymmetrical? Let's draw X and Y axis on it. If I try and flip it over these x-axis, is there a mirror image above and below or left? No, there's no H over here, no H here, not symmetrical. That's how I know it's polar. That's how drawing it can help. If you draw it correctly and you look at the X and Y, you can say, oh, it's not symmetrical, right? So it's asymmetrical, so that's how I know it's polar. All right? Now the way we actually draw this here, this is how we draw it, but the way we can get like a finished drawing, these two here and these two here, the dot and the X, that's our covalent bond. So it kind of looks like this. It's just a single line. So that single line is called a single covalent bond. Let's label that. That's called a single covalent bond. Sorry, I'm getting real messy at the bottom there. So just so you guys can see it a little better, okay? That's a single covalent bond, that's a single covalent bond. So label that in your notes. That's called a single bond. I will stop saying covalent eventually. It's just called a single bond. Single covalent bond, how do we show that? Just a line, a dash, whatever word you want to use. Now, the important thing to remember though is that those electrons here are being shared by H and O. They're sharing them. So oxygen gets neon's configuration, 2-8. It shares one from here, so it has a complete octet, 2, 4, 6, 8. Hydrogen gets helium, 2 electrons, because it's gaining one from oxygen. Now, I don't want to use the word gaining, sorry, I shouldn't say that. They're not gaining or losing, they're sharing. They both share those electrons. That's what covalent's all about. Questions? So I'm hoping you picked this up when we did ionic, so this isn't as hard. All right, you can just learn the new material that applies to this, but the dot structures are the same. No charges here. NH3, how many dots for N? Anybody? 5. 5 dots. 1, 2, 3, 4, 5. I like to put my dots on top. Those 2 dots I like to put on top. You don't have to, but that's just how you're going to see it most of the time. So you have 3 dots that are not bonded. Luckily, there's 3 hydrogens. One goes here, one goes here, and one goes here. There's my dot structure for ammonia. That's it. Is it symmetrical? No. It is on the y-axis. I can flip this way, and that's fairly symmetrical, but there's no mirror image of the H. They're those lone electron pairs, what we call it. That doesn't bond, they don't bond, so that's not symmetrical. So again, asymmetrical, that means it's polar, okay? That means it's polar. And again, if we want to show the bonds, it looks like this. Dash, dash, dash. That's how the dot structure looks, showing the bonds. So on a Regents, a midterm, a test, quiz, whatever, if I ask you to do a dot structure, you can actually do either one of those. The Regents will take either one. The ones with the bonds or the ones with the dots. As long as you're showing the dots that don't bond, you have to show those dots on the O, those dots on the end. You can't just leave them off. They have to be there. Electron configurations. This is 2, 8. That's neon, and then each H is 2 again. I'm not going to do that for each one. It's the same thing we've learned before. That's why they bond. They bond to become stable. And that's why they do it. So before they bonded, were they stable? No, what do you call that? Unstable. So when the H and the O were separate, or the N and the H, they're unstable. They come together to form a bond, they're stable. What do you think has less energy? Something stable or something unstable? Less energy. Stable. Remember the excited state? Electron does what to jump up? Gains energy. That's unstable. It has to come back down. It releases energy. The same thing with bonds. When these compounds and molecules form, they actually get rid of energy. They get rid of energy when they form stable bonds. I'm going to talk more about that tomorrow. But that's a concept. When things are stable in chemistry, they have low energy. That means they got rid of energy to do it. We'll talk more tomorrow. All right, CCl4. Let me create some space here. CCl4, how many dots for C? 4. Germ, how many for Cl? 7. Eyes up here, please. I'm going to put 1 Cl here, 1 Cl here, 1 Cl here, and 1 Cl there. I used X's for carbon. Carbon has 4 dots. I use the X just because there's less dots, so I feel like are easier to make. So 1 here, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I'll give you a minute. Make sure you copy that down. Don't be lazy and leave dots off. You got to keep the dots around the Cl. That's the most involved you would have to do. There's a lot of dots there. 7, 7, 7, 7, 28. There's 32 dots there. That's a lot. That's what I did. Is this symmetrical?
Yes.
Yes. Don't worry, Cal. We got time. This is symmetrical on the X and Y, mirror images, okay? Some kids like to argue, yeah, but the CL, it's not about the actual letters. That's just what we assign to these things. They're actual little spheres, atoms, so really it's a sphere here or a ball, 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 so there's that argument. So this is symmetrical, right? That means it's nonpolar. Everything is equally distributed, it's balanced, all the stuff we wrote down. I'm using the dot structure to help you see that. I think you can see all those words and terms match the dot structure. I hope so. Carbon would be neon and chlorine would be argon. They would share these electrons. Notice how they all have 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8 are on all of them. Full shell. Fluorine. Oops, sorry. Looks like that. Yeah, I did. So this one too would look like this. 1, 2, 3, 4 bonds to 4 Cls with the dots. And yes, I even get annoyed with this. It's just a lot of dots. But that's how it would look with the bonds. There's fluorine. Here's fluorine with the bond. And they all have single covalent bonds. All of these examples. I'm going to give you 3 more examples that have double and triple bonds. Because they exist as well. No such thing as a quadruple bond. So, anyways, back to this. F2 is symmetrical. Here's F2. Very boring. There it is. One F bonded to another. Very symmetrical. Okay? That's F2. It's linear. Okay? So it has symmetry. It's symmetrical. All right, you can split it X and Y axis. It's symmetrical. So it's nonpolar. Everything's balanced, shared equally. The difference in electronegativity for this would be what? 0. 4 minus 4 would be 0. Questions?
Are those single covalent bonds?
Yep, that's single, single, single. Yeah, if you see one line, it's a single bond. Yep. Good question. Any others? All right. Okay, so those are the easy ones.
Right.
Now the hard ones. Hopefully I have time to do this. Here they are. CO2, O2, and N2. Those are the 3 tricky ones. We're going to do CO2 last. If we don't get to it, we'll do it tomorrow. All right, let's do O2 first. So draw 1 oxygen. You let me go? Okay, how many dots does O have? 6. Draw it the same way I do. 1, 2, 3, 4, 5, 6. I know I just broke my rule, but whatever, stay with me. I'm going to put the other oxygen right here. I'm going to use X's. So it's a mirror image of itself. Why it's nonpolar. It looks like I made it a little bit bigger, but whatever. Okay. What's the problem here?
There's still a blank.
Right. You can't have dots by themselves in dot structures. They have to pair up. How many dots does this oxygen have right now?
7.
How many are surrounding it? 7. 1, 2, 3, 4, 5, 6, 7. This one has 7 too. 1, 2, 3, 4, 5, 6, 7. How many do they want? 8. What's the only solution?
Take the other 2.
Yes.
Connect them.
You take these 2 and bring them in and they bond, and that looks like this. That's called a double bond. And then down here, it actually looks like an equal sign. That's what oxygen gas looks like. That's what you breathe. That's what keeps us alive. O2 with a double bond. The double bond is shared between both atoms, so that's now how they get 8. 2, 4, 6, 8. 2, 4, 6, 8. That's called a double bond, so make sure you write that down. Double covalent bond. I'm just not going to write it, sorry. Double covalent bond. You see the 2 lines, which is 4 electrons now. 4 electrons. That's called a double bond. Okay, let's try and get nitrogen done. We're not going to have time for CO2. Here we go. Nitrogen has 1, 2, 3, 4, 5 dots. Put another nitrogen right next to it because they're bonding together. It has 2 dots by itself per nitrogen. That's a problem. So guess what it does?
It makes 3.
It makes a triple bond. These 2 bond, then these 2 come in over the top. 1, 2, 3. 1, 2, 3. That's your triple bond. 3 dots, 3 X's. 3 from this one, 3 from that one. And then you have the 2 dots on top still. Don't forget those. 2 dots on top. Stay there. And that's a triple bond. I've never seen, maybe once. So I've hardly ever seen any double or triple bond structures except these 2 and then CO2. We'll do that tomorrow, but these are the only ones I've seen on a Regis. All right, and the reason they make those double or triple bonds is to become stable. All right, don't forget your homework. I'll be after school reviewing, and tomorrow we'll pick one of you to show how strong you are.
Wait, what? Your thing.
Yep.
You always